We have the lab test on Wednesday. Those are pretty easy to study for, right? Like, and then Friday, we have the fourth test, the last test. It's really no different than the other ones. They're all cumulative anyways. Right? Yes? God, I don't. But by the end of today, it will be posted. And Wednesday, you will get it back. I'm almost done with it. And then Thursday, this would be the 10th. So this is during finals week. There's an optional, well, I don't know if you should talk to Meredith about whether it's optional. From my perspective, it's optional. It is just a hour and 45 minutes of AP test review. Yeah, well, it's not really a class because, well, it's a different day than our class and it's during finals week. I'm not doing anything else during finals week. So this class is done this Friday, and then next Thursday, I know. Yeah, right. If you look up at the board, you'll see that there's a lab exam on Wednesday and an exam on Friday. And then next Thursday, a week from Thursday, is the AP review that it's fine with me if you skip school that day, but it might not be the same to Meredith. Yes, but all of the exams have been that way. Yes. Yes. Oh, yes, sure. If you want to, I will take homework all the way through a week from Friday. That's a good thing to put up here. Oh, but you are missing some? Yeah. Oh. Okay, I'll try to get all your homework up to date this week. Yeah. Okay. Yes. Nope. And it's all in the syllabus, but each one is 10% of your grade. Really? Oh, wait. 12.5%, right? They add up to 50? Okay. Thank you. So homework can be turned in until Friday, 5/11. Exclamation point. Yeah. Yeah. Oh, yeah. In case you were afraid you wouldn't have any physics to do after this Friday.
Was this the last one?
No, one more. Due Friday. Okay. So, who has homework questions? Okay, give them to me. Lay them on me. Okay. Okay, rigid body kinetics number 1. So there's this triangle. And there's 100 Newton force here. And 125 here. And 160 here. And this point is A and this point is B. And I think it just asks, yeah, the total moment about these different points. And this distance is 2.5 meters. And this distance is 1.2 meters. Well, let's first calculate the moment about A. So that's equal to the moment about A from the 160 Newton force plus the moment from the 100 plus the moment from the 125. So if our about point is A, what's the moment produced by the 100 Newton force? 0. What's the moment produced by the 125 Newton force? 0. How do you know that one's 0? Yes, move it along the line of action, and it. That's right. That's like pushing on the end of a screwdriver towards the end of a wrench. Think of it. Oh man, I almost drew it as an octagon. That would have been embarrassing. So how well would it turn that bolt if you applied a force like that? You know, it would not turn. And the reason is that the line of action of this force goes through the about point. Yeah. Okay. Whoops. Okay, so now how do we calculate the moment of the 160 Newton force? Yeah, move it along its line of action is the easiest way until it's just right above this. And then your row vector goes from A to that point. And so then you have a moment arm of 2.5 times a force of 160. And then you have to think, is it clockwise or counterclockwise? That would make it rotate counterclockwise, so it's positive. And so A. For part B, we're going to do it about point B. Okay, so if that thing has an angular acceleration due to those moments, which way would the thing start to rotate? Counterclockwise. Yep. When you do that, it's clockwise to me, by the way.
Oh, yeah.
But no, you're right. I only said that because that's a problem, like the thing I was talking about with the right-hand rule. Yeah. That's like a problem when you go to 3D. Clockwise and counterclockwise don't mean anything anymore. Trippy. Right, only if you have like a reference direction you're looking.
So, if you move it up along its line of action and it reaches the point where the force is being applied, then it's 0?
If you move forces along their line of action, yeah. and if the line of action goes through the about point, then the moment is 0. It's the same thing as trying to turn a wrench this way.
So that 125 is 0?
It has 0 moment because its line of action goes through the about point. The 100 is at the about point, so that one doesn't do anything. Right. That's right. But that easy calculation of just the magnitude of rho times the magnitude of the force, that only works if those forces are, if those two vectors are perpendicular. So if you move the force along its line of action to where they're perpendicular, you can do that easy calculation. Otherwise, you have to use the cross product, either with the component thing or with the sine of the angle. You can. you can always do that, but sometimes it's harder than doing it the other ways.
Oh, okay. So forces, that makes it really easy because you never have to.
Right, but sometimes you have to move it along its line of action if those things aren't horizontal and vertical and stuff. Yep. So this one, there was no, we didn't know anything about the mass or anything. Center of mass. It has to be the center of mass. Yes, that's right. And then for part B, now we're talking about the sum of the moments about B. So what's the moment produced by the 100 Newton force around B? That drawing's starting to look sort of cluttered, but 1.2 times 100, that's right. And then you have to think about, so 1.2 times 100, and then if you applied that force and the hinge was at B, it would rotate it clockwise, so this is negative. Okay?
Why are we calculating forces from A to B if it's rotating just around B?
Because that rho goes from the about point to the place where the force is applied.
But the force is applied.
But we're doing them one at a time. So first we're doing the moment produced by that 100 Newton force.
I see. Okay, so it's 3 different.
Yeah. You calculate 3 different moments and add them up. Yep.
Oh, and then the one towards B will be nothing. And the
Right.
one up there will be
Something.
0.5 times 160.
Right.
Okay. And
Yep.
how do you know if they're negative and positive?
If the force would make it rotate counterclockwise around the about point,
Also, like if there were no other forces.
right.
Okay, that makes sense.
So you just sort of visually do it. Yes. Okay. Yes. Because I moved it along its line of action so that rho and the force would be perpendicular. And I did that so that the sine of the angle would be 90, and we could just multiply those two. But you could do it with the rho vector going from A to the point, and you just have to calculate the angle between them and take the sine of that angle, which is kind of a, it's a pain compared to this. If you can just visualize moving it along its line of action until they're perpendicular, and if that's easy to do, then that's what you want to do. If you do this, yeah, you can do this instead of doing the cross product. That's right. And the reason for that is that the cross product is the same thing as multiplying the magnitudes of these times the sine of the angle when you put them tail to tail. And so if they're perpendicular, sine of that angle is 1, and it's just the same thing as multiplying those forces. Okay. They're not forces, those two vectors. Any other questions right now? Okay, so all we've done so far is calculate about the point B. We calculated the moment produced by the 100. So now what's the moment produced by the 125? 0, because that acts at the... So why was it that when the about point was at A, this one was 0? I mean, that one's acting at what was the about point. So that makes sense. But this one wasn't acting at the about point, but the moment was 0. What's different this time, where now with the about point here, this one has 0 moment, but this one doesn't? Why can't we move this one along its line of action to there? Yeah, because its line of action doesn't go that direction. That's the issue. The line of action of that 125 goes right through A. And then the last one, what's the moment produced by that 160? So you can move that along its line of action, this time this way, until the force is perpendicular to that row vector. And so you get 2.5 times 160. Is it clockwise or counterclockwise? Yeah, only if you're looking at the back of the clock. Then you're right, but don't do that. So this is positive. And so now the total moment, you add these all up. So that's 400 minus 120 is 280. So in which of these cases, if the hinge was at A or if the hinge was at B, in which case would you get more angular acceleration of this thing? A, yep. So no matter what its mass was or whatever, if it's the same object, you get more angular acceleration with the hinge at A than you would at B. Any questions about that? And then number 2, we have this rectangular object. This dimension is 1.4 meters. This is 3.8. And then we have a 200 Newton force here, 250 Newton force here. This says assume gravity acts downward. So, toward the bottom of the page. That's sort of a useless wording. Obviously, gravity acts downward, but I meant toward the bottom of the page. So you have to put it at the center of that object. And it says its mass is 10 kilograms, so this is 98.1. And then it rotates around a pin or a hinge at that point. That's the about point. And we want to calculate the angular acceleration. Yes, that's right.
How do we know this when we just do the row times force?
Well, so the thinking is really exactly the same as with Newton's second law. I could have asked you for a net force in kinetics problems, and then you just add up the forces. But if I gave you forces and asked for an acceleration, you know that the only way to go from forces to acceleration is Newton's second law. So then you need to. So for this kind of problem, you use that rotational version of Newton's second law, where you add up all the moments, and those are equal to I times the angular acceleration. Yes, that's right. It actually acts everywhere, but once you choose a body to isolate, you can treat it like it's acting at the center of mass. All right, so let's do this calculation. Well, first, let's calculate the mass moment of inertia. So the mass moment of inertia for a rectangle is 1/12 times the mass times the length squared plus the height squared. But that's the one about the center of mass. So now we need to use the parallel axis theorem. So the parallel axis theorem says we have to add on the mass times the square of the distance from the center of mass to the about point. The Pythagorean theorem says the square of the distance from the center of mass to A is the sum of the squares of those two components. Know what I mean? Know what I mean, Vern? Do you remember that show? Do you guys ever used to see that show? Ernest Goes to Camp and stuff? Huh. Okay, don't waste your time. I don't know. That was like popular when I was. Know what I mean, Vern? Okay, so what's the vertical leg, the length of that vertical leg of that triangle? It's half of 1.4, so yeah. And then 1.9 squared. So there is your answer. Can someone calculate that? Ooh, that's big. Kilogram meters squared. And so now we can add up all the moments. So that rotational version, yes. So this is the parallel axis theorem, so that has to be the mass of the object times the square of the distance from the about point to where the force is, square of the distance from the about point to the hinge, or the pin, that it's rotating around. And so that means the square of this distance, the hypotenuse. And so I just use the Pythagorean theorem. The square of the hypotenuse is equal to the square of this plus the square of that. Okay, so now let's calculate the moments that each of these forces produce about A. And actually, let's draw a free body diagram. This isn't really a free body diagram yet, it's close. It's a good idea. It's a good idea always when you're using Newton's second law, and when I say it's a good idea, then what I mean, I guess, is yes, you do have to. For my tests. But I can't control what you do after that. For my tests, you have to. For the rest of your life, it's a good idea. Okay, so we have this force. What's that force? That is the contact force between this thing and the pin, or the hinge. And we have this force of 98.1, this force of 200, and this force of 250. There are no other forces. Maybe you're thinking of a different problem. I don't think there is any other one. The height is 1.4. Okay, so let's calculate the moments of each of these. So remember, our about point is this red dot. What's the moment produced by Rx and Ry at that red dot? The moment is either, so these moments are always Z components. So we'll just write it as numbers. Okay. Oh, I see, yes. So those we didn't have to worry about, and we never do. In the free body diagram, they should be in there, yeah. What about the weight force? Yep, that's right. So that can move along its line of action to the bottom. So that's 1.9 times 98.1. And is that clockwise or counterclockwise? Clockwise, so that's negative. And then the 200 Newton force, what's its moment arm? Moment arm? Oh, The row vector? 3.8 times 200. Clockwise or counterclockwise? Yep, so positive. And then the 250, what's its moment arm, row vector? Yes. And that's right. Yes, and so now we've added up all the moments, and those are equal to the mass moment of inertia times the angular acceleration. And so, can someone calculate what alpha is there? Positive 4.04 radians per second squared. And so from that, we know that when you combine all these forces, this thing will rotate counterclockwise because we got a positive moment. Its angular acceleration will be counterclockwise. And then if you wanted to calculate the acceleration of a specific point on there, then you'd use circular motion because every point on this body is in circular motion around the hinge. So now you could use this angular acceleration and the circular motion equations if you knew the angular velocity to calculate the acceleration. Any other questions about that one? Sure. Yes. We did the carousel one, or did we do it?
Yeah, we did the carousel
Okay.
one.
7. Wait, didn't I do 7? No? Okay. Bless you. So we got a rectangular object, and its dimensions are L on this side, W on this side, it has an angular velocity, lowercase omega, angular acceleration, alpha, and it rotates about a fixed point at the center. So everything's rotating around this point. And we want to calculate for this point A, what's the velocity vector and acceleration vector of that point. Okay, so drawing it is not too bad. Yeah, let's use a different coordinate system. Yes, that's a good idea. Did any of the rest of you think of that? Okay, so that point A is in that circular motion. Okay, so let's choose a coordinate system like this. Why not? We can do whatever we want. Okay, so if the angular velocity is omega, we're assuming it's counterclockwise because the sign convention says a positive value of omega would be counterclockwise. And same with alpha, we're assuming that's counterclockwise. So if these are both counterclockwise, what would be the direction of the velocity vector of this point? Yes. So that would be the velocity vector. what would be the direction of the tangential acceleration? What would be the direction of the centripetal acceleration? And so now we just have to use the formulas. Tangential acceleration magnitude is the angular acceleration times the radius. So we do have to calculate this radius.
So basically, it's just the omega.
Well, centripetal acceleration is going to be omega squared times r, but that's the idea. So r here, r is the square root of L over 2 squared plus W over 2 squared. So those both end up being over 4, and you can pull that out and get alpha over 2 times the square root of L squared plus W squared. That's, you learned that in 7th grade. Yeah. And so the tangential acceleration vector, that's in the positive y direction. So we got 0 and then alpha over 2 times square root of L squared plus W squared. And then the centripetal acceleration is omega squared r, which is omega squared over 2 times square root of L squared plus W squared. And that's in our negative x direction. So the centripetal acceleration vector is negative omega squared over 2 times square root of L squared plus W squared, 0. So all together, the total acceleration is, you'd have centripetal acceleration in the negative x direction, tangential acceleration in the positive y direction, Any questions about that? So that's circular motion. I mean, the trigonometry is a little more tedious than most of the problems we did in circular motion, but the ideas are exactly the same. It's just revisiting circular motion. Yes? No. I mean, we chose this coordinate system, so we're good. I have to be able to follow it. So a lot of times I can tell from what you do what your coordinate system is, but you have to make it so I can follow what you're thinking. Any other questions about that one? Okay, let me do one more type of problem that's pretty common with rigid body kinetics. a lot of times you use this to figure out how forces are just like there'll be multiple contact forces on a body, and you want to figure out how they're distributed. So here's the last example. Okay, so here's Jill biking to school. Oh wait, you have arms, right?
Last time I checked, they do. Yeah, I have some people glasses.
Those are your eyes.
Oh, those are my eyes. Got it.
She doesn't care about that.
She's not wearing.
Yeah, well, it's not on her. It's right there.
She would just rather wear sunglasses.
Okay, there's your helmet.
Thank you.
Wow. I was kind of confused.
So let's say the weight is 500 newtons. Is that mg? Yeah. And the question is how much, oh, and I need to give some dimensions, but how much weight is supported by each wheel? Yep. I mean, there's really only two things that matter here. So if the center of mass is here, all we need to know is the distance to where that wheel contacts the ground and the distance to where that wheel contacts the ground. So let's say this is 0.4 meters and this is 1.2 meters. Let's isolate the whole combination of Jill plus bike. Yeah, it would have been more significant before, when it changed everything. So there's a downward force of 500 newtons. There's an upward contact force, the normal force applied to the back wheel. So I'll call that R rear. And then there's an upward contact force, RF, front reaction. Kinetics. Anything that has forces in it is kinetics. Yeah. No. Just so kinematics is just relationships between the motion variables, accelerations, velocities, and positions. And kinetics combines those with forces and moments. And normally we would have to calculate the mass moment of inertia. That would be really an issue here, right? But the good thing is, you know that when someone's riding a bicycle along, what's the angular acceleration? Nothing. They're maintaining the same orientation the whole time. So alpha is just going to be equal to 0. Yeah, when you have angular acceleration on a bike, things are going badly. That's true. But she wasn't, fortunately. So that means that if alpha is equal to 0, we don't need to calculate the mass moment of inertia, because mass moment of inertia times alpha is still 0.
It's 500 the force is pushing that.
That's the weight force.
That's just, how would you calculate?
That's the weight force of her plus the bicycle.
Oh, so
Yeah. And so now we'll go to the rotational Newton's second law. We can choose any of these as the about point. Let's choose, I don't know, let's choose this as the, so let's say that our coordinate system is moving along with the bicycle. Okay, that's fine because that's still an inertial coordinate system. What are the requirements for an inertial coordinate system? No, it can be moving. It just can't have, the origin can't be accelerating and the orientation can't be changing. So having a coordinate system moving with a constant velocity is perfectly fine. Yeah, so really, so you can think of this as, this calculation is the same as if you were just balancing there without moving. And that sort of makes sense, right? Like moving shouldn't change the forces. So if that's the case, then every point is fixed in our coordinate system. So let's say this is the about point. What's the moment produced by the force RR about A? Yep. What's the moment produced by the 500 Newton force about A? Yep, 0.4 times 500, and then is it clockwise or counterclockwise? Clockwise, so negative. And then what's the moment arm for the force RF? 1.6 times RF, and that's counterclockwise, so positive, and all that's equal to 0. So RF is equal to, so that's 200 divided by 1.6. Okay, so RF is 125 newtons. Now how do we get RR? You could, yep, you could do the same equation again with a different about point, or you could use Newton's second law. Newton's second law says there's no acceleration. So if you use the y components of Newton's second law, you know that RR minus 500 plus RF is equal to 0. So RR is equal to 375. So, you know, this just was an issue for me today on my bike ride here, because I have 32 spokes on both of my wheels, you know, basically like my front and back wheels are both the same strength. And you know, I don't know exactly what the geometry of the bike is, but you are a lot closer to your rear wheel than your front wheel. And so your weight is much more concentrated over your back wheel than your front. And my back wheel just today, it's like wobbling. It's like out of true. I got to fix it. It always happens with the back wheel because your back wheel is always supporting a lot of weight. Well, that's not why, actually,
That's not why,
but
that's the
they are over it more, the racers, yeah. But that's what I get for,
resistance in
yeah, right. But that's what you get for having for being a 210-pound man with 32 spoke wheels. Got to build a better wheel for it. That's a good idea. Except our 3D printer can only print stuff that's 12 by 12 by 12, I think.
Well,
so.
you can try.
It's like a little bike.
Yeah, little mini bike, like a circus bike. I'd be like this. You know, it'd be so relaxing.
Like a little arm.
Okay. So the cross product. There are two ways to do cross products. There's the component way, that's basically just a formula, and then there's the sign way. So let's say that you have, an object. You have a rectangular object, and let's say that you're rotating around this point, and there's a vertical force of 600 newtons and a horizontal force of 800 newtons. What's the moment about A? That M has too many lumps. Okay, so in this case, since you have components for this force, the easiest way is to use the formula. You just need to come up with the we need dimensions. Let's go 1 meter and 0.3 meters. Okay, so the rho vector is negative 0.3, negative 1, and then 0, z. The force vector is 800, 600, 0. And so then the moment is the cross product of rho and 800, 600, 0, that's F. So you get 0, 0, and then the z component says negative 0.3 times 600 minus negative 1 times 800. So that's 0, 0, 1.8, so 620, negative 620. And then that z component is what we would use in the calculation. All we're looking at in planar problems is z components. Does that help? Otherwise, you could think of these as individual forces. I mean, really, you can do this without the cross product. I don't know. Sometimes you can get around doing cross product all the time, but when you start doing problems with a lot of forces at random angles and whatever, it gets a little easier, I think, to just use it. But notice, like, you could think of this as two separate forces. You know, it's a force vector, but you could also think of it as a horizontal vector plus a vertical vector. And so then you can just say, move each of these along their line of action to do the calculation. So this would be Move this one up to here. Then you have 0.3 times 600, and that's a clockwise rotation. So that's negative 1.8, 180. And then this one, move it along its line of action to here. You have 1 times 800, that's counterclockwise. So 800 minus 1800, 620, the same as we got before. So in this class, I think that's what I sort of was thinking about your question, Ron. In this class, you can get by without thinking of it as a cross product, I think. In the future, like when you get into three-dimensional stuff and stuff that isn't sort of pre-cooked problems that, you know, then yes, you'll want to use the cross product sometimes. Okay. Okay, so now we're going on to Newton's law of universal gravitation. He has so many laws. He's like a police state. For this topic or for the law? Just for the law, no, it's very short. Yeah, it isn't too hard to understand. If you have, so any two objects with masses m1 and m2 exert equal and opposite gravitational force on each other. They don't have to be opposite in any way. They just have to both have mass. Equal and opposite gravitational force. It's always an attractive force. Like, ooh, look at that force. I'd like to get to know that force better. And the magnitude of this force, so we know the direction is always away from the chosen body toward the other body. They're pulling on each other. It's like a pulling force. F is equal to capital G times the mass of m1 and mass m2 divided by r squared. Yes. Where G is the universal gravitational constant. That's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And r is the distance between the two objects. Yep. Well, yeah, they don't believe that there's such a thing as gravity. They do? I've never heard that one. I think they believe different things. Some of them just believe, like, I don't know, it looks pretty flat. Okay, so here's a couple things to notice about this. Yeah, times 10 to the negative 11. Right. Yeah, exactly. So first does depend. So the gravitational force on an object does vary linearly with its mass. So I wasn't lying to you about that. Yeah, for now we're thinking particles, and yes, it is the centers of mass. Yep. The centers of mass, that's right. Yep. That's right. And everybody in here is exerting gravitational forces on each other, but they're so small. But they can be measured with coolest experiment. I mean, the coolest experiment. And so I'll talk about it, but it's called the Cavendish experiment. And we actually have it set up in the lab, but it's a very complicated experiment that takes a long time to understand. And so we never got into it. But it's sitting up on top of the cabinet, a way to measure what you're measuring really is that gravitational constant E. It's two lead it's two little lead balls and one like big 10-kilogram lead ball, and the two little ones are on just a skinny little wire, thread, and you displace that thread, and it just barely, it's so thin, but it just barely tries to get that thing back in place, and it overshoots and does this very slow oscillation that takes like an hour to swing back, or 20 minutes or something. But I mean, like not like seconds, but like parts of an hour, and that's true. Um, but then that the rate of oscillation is affected by that, because the force of that restoring force is so little on the wire. That attractive force of the 10-kilogram mass actually affects its motion, and based on curve fitting, basically, like you can figure out what that constant is. And so somebody measured that universal constant of gravitation in like 1800 or something. It's amazing. That's Cavendish. Yeah, it's amazing. And to see it work is amazing. Okay, so that's what I said before. But what I didn't say before is that this gravitational force also depends on the distance between the objects. Right, so we'll talk about that. And that, well, it's still conservative. Yeah, it's still conservative, but it's not constant. So the potential energy then is well, it's like the derivative with respect to negative derivative with respect to r of this. So negative g m1 m2 over r to the negative third, right? No. Over r. How does that work? Okay, that's not what I said anyways. So it does depend on the distance between them. And up until now, we've been saying that no matter how high the object is, or in other words, how far the object is from the Earth, gravity pulls on it the same amount. So let's figure out, so why have I been saying that? And presumably we've been getting pretty good results, you know? Yeah, right. The farther you get from the center of the Earth, the farther you get from the center of the Earth, the less it's pulling on you. That's right. So if you're in a spaceship in orbit, you know, orbit depends on gravity. So obviously you're not really free of gravity, but gravity is less as you get farther away. Okay, so why do we usually treat the gravitational force as independent of the height? Hey, listen. Hey, see you tomorrow, right? Yeah. What? So why do we usually treat the gravitational force as independent of the height?
Radius of the Earth is so big
Yes.
that if you move it, okay, but relative, like the climb to the mountain is like tiny in the scale of the
Yeah.
space.
So let's just figure out what the difference is as you move a mile vertically. Yes. So how much does the gravitational force change if the height changes by a mile?
Well, the diameter is 3,963 miles, or the radius, sorry.
So let's say 1 mile above the surface of the Earth. What did you say? Did you just know what the radius of the Earth is?
No, it's in my
Oh, okay.
It has the
That was amazing. Now I realize it wasn't amazing at all. Okay, so at the surface of the Earth, the force is the gravitational constant times the mass of the Earth. I'm going to call that m. Times little m, divided by the radius squared, and the radius of the Earth is 6.371 times 10 to the 6 meters. We're squaring that. So now 1 mile above the surface 1 mile above the surface, we still have the g, the mass of the Earth, the mass of the object, but now the radius is 6.371 times 10 to the 6 plus 1609, and that's all squared. So that's what, oh yeah, so for all you guys who run mile, that's how a true mile is 1609.344 meters. So you run 1600 meters, so you're 9.344 meters short of a. So actually, I think every race for the rest of the season, you should just run right through the tape for 9 more meters and then stop your watch. That would be like a totally studly move. And everybody's like, oh no, I'm running the mile today. Yeah, I won the mile. Yes? That's the G value. The radius of the Earth is this. Yeah, I wouldn't know that. It's in my notes. There was a guy from Burnsville. You guys you wouldn't remember this, I guess, but I think it was about 2008. Rob Finnerty, yeah. And he ran the state record for the 1600 meters in 3:59 for 1600 meters. And at that time, only 4 people in American history had ever run sub 4 minutes for the mile in high school. But that was for the 1600 meters, and if you do the standard conversion for how long it would have taken him for the last 9 meters, his time was like 4:01 point something, and so he just missed it. He had to lose her, exactly. He was pretty fast. Okay, so let's figure out the ratio then, so Fs over F mile, a lot of this stuff cancels out, and you just end up with 6.371 times 10 to the 6 plus 1609, whole quantity squared, over 6.371 times 10 to the 6 squared. And you get that the force of the surface is 1.00051 times the force a mile above the surface. So up to a lot of precision, even a motion of a mile vertically doesn't have any significant effect on the strength of gravity. Any questions about the thought process there? So all the M's and the G all canceled out, and we just got left with that stuff, and that comes out to be basically 1. If it was 1, then they would be exactly the same. Yep. Yeah, so the thing that affects it more than altitude is apparently just geological formations. Uh-huh. Yeah, and then if you're close to mountain ranges or something, I think gravity is higher. But yeah, it does vary a little bit. Uh-huh. Yeah, exactly. Yeah, exactly. That'd be a good idea. Let's go. I pole vaulted 10'6". Yes. It's not that good, but yeah, it's pretty dangerous. People get hurt pretty Okay, let's. Okay. Well, we know that. So it's still a conservative force. So there has to be a potential energy function. And we know that the force, G big M little m over R squared, has to be equal to the negative partial derivative with respect to R of U. And so we can integrate this, and we get that the potential energy function is, whoa, that was crazy. Potential energy function is negative G big M little m over R. And so let's figure out what are we going to do first. So let's use this to figure out the escape velocity if we ignore air resistance. Yeah, to never fall back down. How fast do you have to jump so that you never come back down? Yeah, because I know I've jumped 3 meters per second before and I came back down, so it's more than that. Okay, so think for a second. Okay, so we're going to use conservation of mechanical energy. So at instant 1, we're at the surface of the Earth with some speed v. So the kinetic energy is 1/2 mv squared. The potential energy at instant 1, we're at the surface of the Earth, so this is going to be G times big M times little m over the radius of the Earth squared. And at instant 2, we're talking about the highest point this thing gets to before it starts to come back. So what's the speed at that instant? 0, yep. So kinetic energy is 1/2 mass times 0 squared, so 0. And the potential is, so that's going to be the distance r, like how far away you are. Maybe I'll call it h. You know, that's that highest height. Oh, these are supposed to be negative. Because that's what the potential energy function is. This is the potential energy function. Oh, and it also shouldn't be squared. Sorry, I was thinking of the force. This is the potential energy function. So, yeah, that's a good question. So when do we need to use this? We need to use this anytime you're talking about distances that are much bigger than the object is way away from the surface of the Earth. You know, if your distance from the surface of the Earth is at least on the order of magnitude of the radius of the Earth, then you have to use this approach. So we'll use it mostly for planetary motion, satellite orbits, that kind of stuff. Okay? For things that are far away from the surface of the Earth. If you're just talking about motions near the surface of the Earth that are the order of magnitude of like our daily experience, you can still use the old approach. It's a good approximation.
Okay.
You were saying that for institute potential energy is just h. Why?
It's not h, the distance is h. So this is going to be negative g, big M, little m over h. So h is how far away the thing gets before it starts coming back down. So conservation of mechanical energy says 1/2 mv squared minus g, big M, little m, over the radius of the Earth is equal to 0 minus g times big M, little m, over h. And we can cancel out the little m's. There's one of those in everything. And multiply everything by 2. And we get that v is equal to the square root of 2g big M over re. Yep, minus 2g big M over h, all square root. So this tells you how fast you have to be going to get to some certain distance from the Earth. Yes? Oh, it won't matter, but that's a good thought. So I guess we're saying that h is a distance from the center of mass, the center of mass of the Earth, the way I have it written there, instead of a height above the surface. Otherwise, yes, you're exactly right. Question? That's the mass of the Earth. So this is general for any body. So your escape velocity from a small mass would be very small. Yep. And now we'll take the limit. So the escape velocity is the limit as h goes to infinity, because we don't want to ever reach that highest point where it starts coming back down. RE is the radius of the Earth, and h is a general distance from the center of mass of the Earth to the object.
So in the first experiment, it's RE because it starts on the surface.
Yep.
And then it goes up to the flat.
That's right. Okay, so what's the limit of that square root as h goes to infinity?
What is big M again?
The mass of the Earth. And do I have a number? I don't have a number for that here, but you could plug in the constant I gave you, the radius of the Earth. The mass of the Earth is heavy. 5.97. That's a great question. Times 10 to the 24th kilograms. That's a big old thing. It's about equal to 11,180.5 meters per second. That's at the surface of the Earth. You need to be at that speed. And it doesn't even matter what direction you're going if there's no air resistance. You can be going horizontally, vertically, anywhere in between. You'll escape the Earth's gravitational pull if you go that fast. That's the kind of practical thinking we need. I just plugged in the values for all this. I gave you a G value before. That's the gravitational constant. Mass of the Earth divided by the radius of the Earth. Square root, and you get that.
We got it already.
Right.
Oh, I thought that was all. That's pretty fast. You gotta get going.
Yeah, it is fast. But, I mean, imagine how dangerous it would be if you... Yeah. Imagine how dangerous it would be if you had like a car that could go the escape velocity of the Earth. Like, every time you went in your car, you'd have to be careful that you didn't disappear into space.
Yeah, right off the engineer.